Okay, a little bit of a short problem for you today. Today we're going to be looking at a ball that's bouncing down a bunch of steps. This comes from a University of Wisconsin qualifying exam, can't remember the year, but classical mechanics problem, projectile motion problem. And what we want to do here is see that these steps happen to have their tread equal to their rise. So this is a square basically. L will be the tread, the size of the step, and then the rise of the step will also be L. This is not a perfectly elastic collision. It would keep bouncing up to the same height if it were. So we have a coefficient of restitution that we can assume is given to us in the problem. And the question is, what's the horizontal velocity necessary to keep this sort of pattern going over and over where it's always bouncing in the same location of the step each time and rising to the same height? And also, what is the bounce height that's needed? That's the height above the step that it reaches its maximum. So the first thing we could do is we could recognize that just before a bounce, maybe I'll call this velocity 1, so that's this incoming velocity right before it hits the step, can be written in terms of these unit vectors, and these were suggested in the problem. I think they're okay to use. I hat will be to the right, and j hat we'll just call positive down to make life a little easier. This will be Vx in the I hat direction, and then plus, let's call it V initial or something in the j hat direction. So V initial stands for the velocity in the initial direction. And then we also have that V2, which is the velocity immediately after the bounce, will have the same horizontal component because there's no friction with the step, so no horizontal impulse, still in the I hat direction. But we'll end up with, well, I'll call it positive, where these V's could be negatives. These aren't speeds, they're components, Vf in the j hat direction. Now what we want to do is try to use either kinematics, dynamics, or energy conservation to find what these have to be. Don't forget, we do have this relationship between E and the two vertical speed components or velocity components. Okay, so let's start with conservation of energy. That's probably a little easier. So if we examine this particular bounce right here while it's in the air, so there's no inelasticity while it's flying through the air, there's no drag or anything like that, I know that by the time it gets down here, it's going to be moving with the speed of v1 again, velocity of v1 again. So the speed here, in terms of its kinetic energy, has to come from the initial kinetic energy right after the bounce, plus this change in gravitational potential energy. So what we have is the initial kinetic energy, well, let's say the final kinetic energy. The kinetic energy right before a bounce should equal the kinetic energy right after a bounce, which will be less because it loses some with the coefficient, and then plus the amount that's gained from gravitational potential energy falling this distance L. Now, notice that when I square out these two velocities, there'll be a 1/2 Vx squared on both sides, so those will cancel out. And I'll go ahead and cancel all the m's. Okay, so here's our relation once we've canceled some stuff, and we're only looking at the y components. But luckily, we've got this nice relationship between Vf and Vi in terms of the coefficient of restitution. All right, so solving this out, let's solve for Vi. And it'll be, what, 2GL? This Vf I can replace with E times negative Vi. The negative doesn't matter since we're squaring it. And then when I pull that over and factor, I'll end up with this relation. Okay, so this is the speed that the ball has to have in the vertical direction, not the speed, I guess just the horizontal, the vertical velocity, right before each bounce. Now let's see how we can relate that back to Vx and H. Okay, let's turn to kinematics to try to work out the rest of this. So let's see. Since the acceleration in the vertical direction is a constant, we can go ahead and write that V1y, and the reason I'm doing it that way is because I'm looking at this velocity right before it hits the step. It's a positive number. It's in the positive j hat direction, which is down, unfortunately. Has got to be v2y plus gt. Okay, why is that? So this is what we're calling vi, and this is what we're calling vf. Now this looks a little weird because sure seems like we're subtracting or something like that. But this will turn out to be what we want because g is positive in the downwards direction, so I had a plus sign here for the acceleration. And then vf is actually my initial velocity right here of the arc. It is in the negative direction, but remember that vf itself is a negative number based on the way we've decided j points. We also have the relation that horizontally, the time between bounces is the tread of the step divided by its horizontal speed. So setting these two times equal, let's see, we'll have what? Vi minus vf over g for the period in both cases. But we have this nice relationship. Let's go ahead and get rid of the vf. So I have vi minus evi over g. But of course, that's going to be vi times 1 plus e. But look, vi has this funky factorization. So I'm going to write this as 1 plus e over g square root of 2gl over 1 minus e squared. And the reason I want to write it like this is when I go solve for vx, this is a difference of squares. So I can factor it as 1 plus e times 1 minus e, which means when I bring that 1 plus e inside, it'll cancel here and be left with just a 1 plus e. Similarly, this g can come inside downstairs. And why not? While I'm at it, this L and this L will also come downstairs. So putting it all together, we have that the required horizontal speed for this pattern to work for a given E is just the reciprocal of this whole thing. It'll be the square root of GL over 2 and then 1 minus E over 1 plus E. Okay, hopefully that makes some sense. Let's see. If E goes to 1 and it's perfectly elastic, well, then it better not be moving horizontally at all, or else it's not going to repeat itself. It'll just kind of bounce with larger and larger arcs each time. If E goes to 0, well, I'm pretty sure that that just doesn't really work, because then the instant it plops, it's just going to stop. So that's kind of curious that they still gave us a GL over 2 in that case. I guess that just makes sure that it still makes it to the corner. And finally, let's work out what the height is for each of these bounces. I'm going to go ahead and use conservation of energy again. So we know that, for example, 1/2 mv2 squared, that's the kinetic energy right after this bounce. When it reaches the top, is going to have to be 1/2 mvx squared. It still has motion there, but it's horizontal, plus mgh. Expanding this out, because it'll have a 1/2 mvx squared and a 1/2 mvf squared, and canceling all of the, cancel the m's in a sec, we end up with just this relationship. Now we can cancel the m's and go solve for h. So h is going to be vf squared over 2g. Vf, as usual, is negative e times vi. So I'll write that as e squared over 2g times vi squared. And finally, we know what vi squared is from this, and the 2g's will cancel. Okay, there we have it. We have our horizontal motion and our max height of each bounce in terms of the parameters of the problem, which are the height/tread of the step and the coefficient of restitution of the ball, QED.